Before looking at this diagram, I'd like to go over a more simple version that you may or may not have encountered in the higher course. It was certainly in the past paper that I sent out. So if we have a look at a typical diagrammatical Hess's law, where we could have, here's reaction A to B, and we want to know how much energy it takes to do this, or what's the delta H for this. But the information we've been given is the value for delta H for this, and a value for delta H for that from B to C. Using Hess's law, as the enthalpy is independent of the route taken. So we want to try and go from A to C and then C to B, because that would be identical to going from A to B, or certainly the energy would be. So to do that, we would add, we've got the reaction from A to C, and we know that our delta H for this is 2. I'm not giving it any numbers just now, I'm just calling it reaction 2. And then we want to go from C to B, which we don't have. What we've got is B to C. So if you were to switch the sides, you switch the sign. So it's like going in the opposite direction up here. So delta H wouldn't be the 3, it would be negative 3. And then by simply adding what numerical values these were, so the numerical value of 2 taking away the numerical value of 3, we would get the delta H for X. Relating what I've just shown you to this diagram here, this one looks more complicated, clearly because we've got these 2 arrows. Converting that diagram into the same style of diagram as I've just done, with no double arrows, we would have our CO2, and we want to find out what X is when that becomes carbon gas and 2 oxygen atoms. We don't have that route, but we do have an alternative route. So this is plus 395 or plus 394, and that takes us from CO2 to carbon solid. Excuse me, I should have put in the gas here, it is important. Carbon solid plus oxygen gas. And then what we can do is we can break this area here into 2 separate steps. So the first one, we can just go with the plus 716. And if you have a look what's actually happened there, we've gone from carbon solid to carbon gas. So that's the only change that's happened there. So that's the enthalpy of what would be called sublimation, where you have gone from solid to gas because carbon doesn't melt. So it's just the energy required to break all the covalent bonds in the carbon for 1 mole and break that and turn it into 1 mole of gaseous carbon atoms. The next thing we're going to do is we're going to break this oxygen molecule and turn that into 2 separate oxygen atoms. So that would be the bond enthalpy for the oxygen, and that, according to the diagram, is plus 498. So if we want to go from here to here, which can't be measured, that's fine. We can just move our way around this way. So we would have plus 394, plus 716, plus 498. All the arrows are going the correct way for us, so we can simply add them all together and you end up with a total enthalpy for this of 1608 kilojoules per mole. This bottom diagram looks even worse because now we don't have any labels. We don't know what's at each of these steps, which way on are you supposed to put reactants and products. So I'll give you a few hints on this. This would mainly be a problem solving activity because Born-Haber cycles are no longer part of the course. However, the SQA is well known for putting in things that aren't part of the course and making them problem solving. So I thought it would be worthwhile going over this. So with no labels on this, we need to find out where to start. And your biggest hint comes from where the arrows originate from, or where most arrows originate from. So here we've got two ends of arrows, which means that this energy level is most likely to be the one where things are in their standard state. So this standard state, if we put that on a diagram over here, their standard state for carbon and oxygen would be carbon solid and oxygen gas. So that's our starting point. And from there, we've got an arrow down, so it's negative 394. But the question is, why is it negative on this diagram, but it was positive on the other diagram? To answer that question, we need to have a look at potential energy diagrams. The ones that look like this. So in these diagrams, the endothermic process is bond breaking, so energy is required to break bonds, but the exothermic process is bond making. Thereby the delta H occurs because of the balance between the energy put in to break all the bonds and the energy released when we make those bonds. So relating that back to this diagram, it's a negative 394 because if you think about what's happening in this reaction, we've got carbon combining with oxygen to make CO2 gas, which is an example of a combustion reaction. So we're effectively just burning our carbon in oxygen, and all combustion reactions are exothermic. So that's why we have the negative. Looking at the rest of the diagram, this time we're going to make changes to the standard state for each of these two individually. So first we'll have a look at the carbon. So the carbon takes energy to sublime that. So that's an endothermic process. That's plus 716. So the only change we've made there is to change our carbon solid into carbon gas. And again, we're going to make the change where we change our O2 for our bond enthalpy for oxygen and convert that into 2 oxygen atoms in their gaseous form. Our carbon has stayed the same. So when you combine all of these processes, or you compare where our starting material if you compare what our starting material is to our final product, then the difference between these two is x. So in this instance, to find x, we would be going against the flow of this, because we're starting from here and we need to make it up through all of this up to here. So we'd be going up 394, so that would change the sign of this, up 716, and then up the 498 kilojoules per mole, which I didn't add on, sorry. And so you add all of those up and you end up with the exactly same 1608 kilojoules per mole. Enthalpy of formation. Standard enthalpy of formation, delta H naught F, of a compound is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states. Now that is certainly a definition that you are going to want to learn word perfect. It's a bit like learning the Hess's law definition or one of the others that we encountered at higher. What's also massively important and applies during all the calculations is this next line. The standard enthalpy of formation of elements is by definition 0. So elements are 0, which gives you the baseline of 0 from which enthalpy changes can be measured. The standard state of a substance is the most stable state of the substance under standard conditions. Standard conditions, as far as we are concerned, is 1 atmosphere pressure, 25 degrees C, which is 298 Kelvin. Okay, for chemistry you do need to know that 0 degrees C is 273 Kelvin. Standard enthalpy change for any reaction can be calculated from the standard enthalpies of formation of the substances in the equilibrium using the equation. So we have that equation there, and that's in the data booklet. And when you have a look at the data booklet, there are a lot of equations that all look very similar. So the process that you're going to learn in the video that's coming up will be very similar for this and this and this. And it's also not too dissimilar a process from the bond enthalpy situation. I'm not going to talk you through all the calculation. I'm going to leave that for the video. However, this last little bit. Any calorimeter experiment requires all of the heat energy lost or gained by the reaction to be transferred to the calorimeter of known heat capacity, which is insulated so that no heat is lost or gained from the surroundings. For this reason, it's very difficult to accurately carry out calorimetry experiments in the laboratory, as there is always substantial heat exchange, whether that's loss or gain, with the surroundings.
Hello and welcome to the Chemistry Solution. This tutorial is on calculating enthalpies of reaction from enthalpies of formation. What is the standard enthalpy of formation? The standard enthalpy of formation is the enthalpy change associated with the formation of 1 mole of a compound in its standard state from the elements composing that compound in their standard states. And so, by definition, the enthalpy of formation of an element in its standard state is equal to 0. Now, in order to calculate the enthalpy of reaction, we can take the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. And in this case, N and M stand for the coefficients in the balanced chemical equations. Let's look at an example. Calculate the enthalpy change for the combustion of 1 mole of glucose to carbon dioxide and water. The first step in doing one of these problems is to write a balanced chemical equation. We know that for a combustion reaction, our compound is reacting with oxygen in the air and producing carbon dioxide and water. We then need to balance our chemical equation. The next step is to look up our enthalpy of formation values for the products and reactants on the table and place them in our equation. Remember that the enthalpy of reaction is equal to the sum of the enthalpies of formation of the products times their respective coefficients minus the enthalpies of formation of the reactants multiplied by their coefficients. Now, in order to do these problems, you would be given a table listing the enthalpies of formation of various different compounds. But in this example, to save space, I've listed only the values that we will need for this problem. The other thing that's important when doing these problems is to specify the state of your reactants and products, because the enthalpy of formation values differ depending on the state of a compound. So, for example, the enthalpy of formation of liquid water is different than that of the enthalpy of formation of solid water or gaseous water. You'll also notice that in my enthalpy of formation values, O2 is not listed. This is because the element oxygen exists in the standard state as a gas, and so the enthalpy of formation value is 0. And this holds true for any element in its standard state. Now let's plug these values into our problem. First, we're looking at the sum of the enthalpy of formation values for the products. Starting with CO2, I can see that the enthalpy of formation value is negative 393.5 kilojoules per mole. And I multiply this value by 6 because 6 is the coefficient in front of CO2 in our balanced chemical equation. And because I use the coefficients in my balanced chemical equation, this is why it's particularly important to balance your equation correctly. Also on my product side, I have 6 water. So I take 6, which is the coefficient in front of H2O, and multiply that by the enthalpy of formation value for water in its liquid form, which is negative 285.8 kilojoules per mole. This is the sum of the enthalpy of formation values for the products multiplied by their respective coefficients. I then subtract the values for the reactants. I have 1 glucose, so I take 1 multiplied by negative 1260 kilojoules per mole. And then remember, I stated that the value of oxygen, because it's an element in its standard state, is 0. These are the enthalpy of formation values for the reactants multiplied by their respective coefficients. And now it's a matter of correctly putting these values into your calculator to come up with the correct answer. Be very careful keeping track of your negative signs and the parentheses so you come up with the right answers. And I think it's best to do these problems step by step, writing out the values you get for each part of the equation along the way. And this leaves me with an enthalpy value for the reaction of negative 2,816 kilojoules per mole. Let's look at another example. Calculate the enthalpy change for the following reaction. Ammonia plus hydrochloric acid goes to ammonium chloride. The first step is to check that you have a balanced chemical equation. and in this case our equation is already balanced. The next step is to plug our enthalpy of formation values into our equation. So we look up the enthalpy of formation values for the products and reactants on the table. On the product side, we have 1 mole of ammonium chloride, and the delta H of formation of ammonium chloride is negative 314.4 kilojoules per mole. On the reactant side, we have 1 mole of ammonia multiplied by the delta H of formation value for ammonia, negative 46.2 kilojoules per mole, and also 1 mole of HCl as a gas, which we multiply by its delta H of formation value, negative 92.3 kilojoules per mole. We then take the sum of the values for the products multiplied by their coefficients and subtract the sum of the values for the reactants multiplied by their coefficients, and come up with the delta H of reaction equal to negative 196 kilojoules per mole. Thanks for watching the chemistry solution. We hope you enjoyed this tutorial.
This thermochemical cycle is very similar to the one I showed you previously. However, in this case, because we're dealing with delta H for formation, we can have a look and see that we've actually got a 0 here. So rather than just being increasing energy with no scale whatsoever, we now have a scale because our 0 is for the elements when they're in their standard form. So carbon solid for graphite and hydrogen molecules, which are gaseous at 298 Kelvin. When setting up a thermochemical cycle like this, it's always important that starting from here, anything that's positive you would add sequentially, one after the other, taking note of what the change is. So this change here, all we've done is turned carbon solid into carbon gas. So this would be the enthalpy of sublimation of carbon. Here we've gone from 2 hydrogen molecules up to 4 hydrogen atoms. So that will be 2 lots of the bond enthalpy for hydrogen. So we would add all our positives, one after the other, going up the way. Then here, we're going negative, because this is an exothermic process, in going from carbon solid and hydrogen down to methane. We have a value for this given in the paragraph above. What's important to notice is that if you treat this as a cycle, which is what it's saying, you can work out what all the energies are, because if you add them all up together, they will end up back at 0 again, because you can head right the way round and head back to 0. So when adding these up, if we started from here and to come back to this point, then we would have plus 715 plus 2 times 432. Then you've got 4 of your CH bonds, which takes you down here. But because this is going down the way, that would now be a negative. And then this one, although this is negative, you need to go the other direction to get back to the start. So that would become plus 75. And all of that together will equal 0. So algebraically, you can solve it to work out what the carbon to hydrogen bond enthalpy is. This last paragraph on page 113 is important. It can be seen in the last 2 examples that the carbon to hydrogen bond enthalpy value and the carbon to carbon bond enthalpy values are different from the data booklet values. This is caused by them being calculated from different experimental data. Often different data booklets have slightly different values quoted for this reason. But why this is important to you is that although you can use, whilst doing these calculations, You can use the data from the data booklet to find your unknowns if it asks you to. But what you can't do is just pick the final answer straight from the data booklet, because you can guarantee that what they want you to do is go through the process of the calculation. So if you just pick an answer from the data booklet, it's not going to be right. It's going to be off slightly, but you obviously don't know how far off or in which direction. So you have to go through the process, even if the answer to the question appears to be in the data booklet. Again, on this thermochemical cycle, please note that your zero energy is starting from where your elements are in their standard form.